Hello, math students. Mr. B here. All right, we are going to do an exponential decay problem. In this problem, we have a radioactive substance that has a half-life of 300 years. If the starting amount is 80 grams, how much will remain after 1,000 years? All right, before we even think about equations and things like that, let's graph the amount versus time, just roughly. Okay, on the horizontal axis, I'm going to have time. Vertical axis is going to be the amount in grams. The time is going to be in years. And we're starting with 80 grams. That's time equals 0. And what does the half-life mean? It means after that half-life, 300 years in this case, there's going to be half the amount you started with. So there'll be 40 grams after 300 years. So I'm going to put a point here at 300 years, 40 grams. All right, if we go another half-life, that will be 600 years after 0. There'll be half as much again. So now we'll be at 20 grams. 20 grams. How about another half-life? That'll be 900 years from 0. Now we'll be at 10, right? Half of 20. That might be here. And then if we go another half-life, we'll be at 1,200 years. And what's half of 10? Well, it's 5. So I will graph that point out here. And now maybe a quick little line, a curve, not a line really, to connect all these data values. And my hand is wiggling badly. Oh well. You get the idea. It's ramping down. It's not a flat line. It's a curve that's smoothly going through all these points. And we can see where we want the amount. We want the amount when the time is 1,000. Maybe that's about here. 1,000. And if I go up to the graph and then over, you can see, it's not too bad, that the amount we want is going to be between 10 and 5. So our amount is going to be bigger than 5, and it's going to be less than 10. So we've narrowed it down a little bit. We're going to have somewhere between 5 and 10 grams when we're done. Okay, let's do this mathematically now and get the exact amount that's going to be left after 1,000 years. The master equation is just like the growth equation. It's the amount at time t equals the starting amount, which we'll call a sub 0, times e to the k times t. Here our k will be negative. And that's what we really need to figure out, what the k is. And so we need some data to put in this equation so that we only have k left to solve for. We need a time, we need a starting amount, we need an amount at that particular time. So how about using the first half-life? Okay, so we could say if we start with the 80, then k at 300 years, that's the half-life, we're going to have 40, right? That's the amount at 300 years, 40. And now we can solve for k. It's the only thing that's not known in this equation. What if we divide both sides by 80? Then we have the exponential alone, e to the k times 300. And on the left side, you can see that we've got 40 over 80. That's actually a half. In fact, it doesn't matter what the starting amount is if you know the half-life. You could just say, okay, the starting amount is a0 e to the k times 300, and the amount after 300 is the starting amount divided by 2. Then you divide both sides by a0, a sub 0, and you're left with a half on the left. So it really doesn't matter that you have 80 to start with. What matters is that the half-life is 300 years and that there'll be half of the initial amount after that time. Okay, so now we have to solve for k. Let's take the natural log of both sides. We're taking the natural log because the right side has got a base of e. Natural log e to the k times 300. And then by the power law, for logarithms, this k times 300 is going to come out and become a multiplier, coefficient. So k times 300 times the natural log of e, and then on the left side is natural log of a half. Now, natural log of e is actually 1 because, log base a of a is 1. Why is that? That's because a to the first is a. Well, we have log base e of e is 1. ln of e just means log base e of e. All right, so that's 1. Hey, we're almost there. All we have to do is divide both sides by 300, and we'll be able to get k. Let me put this in a calculator, and we'll get an approximation for k. K is, well, it's equal to the natural log of a half divided by 300. That's the exact value of k. But we're going to get an approximation so we can approximate the amount after 1,000 years. So let's see here. So we need a natural log of a half and divide that by 300. I am going to keep 3 significant figures. That means after these zeros kind of end and we start getting non-zero numbers, I'm going to keep 3 of them. 0.00231. All right, so that's our k. In fact, we can now write our decay model, which is just saying, we're going to write an equation that will be able to predict the amount at any time t. So it'll be a of t is 80. The starting amount is 80 here. E to the negative 0.00231. And look at that, I am getting a negative k, right? And then there's a t. So this is our model. Now we want to know a at 1,000. So let's put 1,000 in for the time. 80 times e to the negative 0.00231 times 1,000. And I'm going to get an approximation here. Let's see what we get. It better be between 5 and 10, right? Otherwise, we did something wrong, or I did something wrong. All right, so let me get this number in there. 0.00231 negative. All right. That gets multiplied by 1,000. All right, there's that. Got the 80. All right, I am getting 7.94 grams. Hey, and that's between 5 and 10. Kind of like we expected, right? All right, hope you enjoyed that problem. We could actually have solved something like this. I want to come up with a formula for a k if you just know the half-life. It would be this right here if you knew the half-life that was 300 in this case, but if you have 1/2 equals e to the k times, I don't know, maybe I'll call it capital T for the half-life. And you solve doing the same thing. You take the natural log of both sides. You're going to find that k equals the natural log of 1/2 divided by the half-life. So there's a formula you could actually use. But it's fun to just do it by hand every time. Likewise, you could also say that the half-life, if you knew k for some reason, the half-life would be the natural log of 1/2 divided by the k. So if someone told you what the k was, you could figure out the half-life. Maybe I should put a little 1/2 subscript on this T to make it really clear that that's the half-life. All right, there. I really am finished now. We'll see you next time.